This lecture is on group homomorphisms. So I'm going to define it again on a later slide, but just as an introduction, I'll define it here too. A group homomorphism is a mapping. So let's say we have two groups, G and G prime. And I'm just going to, we'll formally define it later. Let's say this is G and G prime, two groups, two sets, two non-empty sets. And I want to define a map from G to G prime. We'll call it phi. And it has to be one that preserves the algebra. So let's see, if I pick A here and B in G, then they will map over to phi of A and phi of B. Remember, a mapping is a function. A mapping means that it picks up each element of G and maps it to one element of G prime. So we have a mapping that tells us that there'll be a phi of A and a phi of B. Now, by preserving the algebra, I mean this. Let me put AB here, and over here, let me put phi of AB. Okay, so AB maps to phi of AB, and if it's a homomorphism, phi of AB is the same thing as phi of A, phi of B. Okay, so notice I'm using multiplicative notation. If I write this, if I write AB over here, I mean A delta B, where delta is the operation in G. If I write over here, as I did, phi of A, phi of B, those are elements of G prime which may have the operation star. So it means phi of A star phi of B. Just think of it, you have to know what group you're in. And whatever group your elements are in, that is the operation. The multiplicative notation indicates that operation, unless, of course, it's addition. So a group homomorphism is a mapping, but it is one that preserves the algebra. In other words, it doesn't matter over here if I multiply A and B and get AB and then map over to G prime, or if I map A to phi of A, B to phi of B, and then multiply in G prime. It doesn't matter if I multiply first and then map, or if I map and then multiply in G prime. That's what it means to be a homomorphism. Now there's one other thing I'd like to include in this picture that I didn't talk about much in the video, but we will in class. Let's say this is G again, and G prime. Every element of G will be mapped to an element of G prime, but not necessarily will every element of G prime get hit. In other words, G may map onto just this subset of G prime, and we call that subset phi of G. Notice it's the image, in other words, the image of G under the mapping phi. The image of G is often written as phi, and if there's a set in there, you know it's not the mapping phi. You're not trying to find another element. It means something different. Phi of the set G means the image of G under phi. So let me, instead of using G and G prime, let me change G. Why don't we call this the real numbers? And over here, we'll call this the real numbers too. We'll have a mapping from R to R. And let's call that mapping phi, but we'll say that phi of x is equal to x squared. So this is just one example. All right, so we're taking all of the real numbers and squaring them. Well, when we square them, we get positive numbers. So in this case, the image of R, the image of R under the mapping phi, the image of R, or phi of R, with this example, is equal to the set of all x in R, such that x is greater than or equal to 0. In other words, R star with 0 thrown in. So out here we have, in here we have the positives and 0, and out here we have the negatives. The negatives are not hit. This is not an onto mapping. It's onto its image, which is a subset of R. Now another thing is this mapping is not one-to-one, is it? Because, for example, -1 and +1 both map to their square, which is the same, 1. So in this case we see phi is not onto R. Every element does not get hit, and phi is not one-to-one. So we're just going to look at some groups with one-to-one onto mappings. In other words, groups that are isomorphic or algebraically identical. And we looked at these in class. Now I haven't formally defined anything yet, but look, we have a cyclic group of 4 elements, Z4, and we have the Klein 4 group. That's what it's called formally, and you have seen it in this form. You've seen it as a subgroup of S4. 1, 2, 3, 4. This little group. 1, 3, 2, 4, and 1, 4, 2, 3. This little subgroup of S4 is an example of the Klein 4 group. In other words, it's a group of 4 elements, and all 3 non-identity elements have order 2. So you can see that these are certainly not algebraically identical, because in the cyclic group of 4 elements, we only have one element that if you multiply it to itself, you get, if you add it to itself, you get 0, and that's 2. 2 is the only non-identity element of order 2, but over here we have all 3, A, B, and C, or in this case, the product of 2 cycles, all have order 2. Now, it's nice to see what you can tell in a table. You can tell if a group is abelian, and you can see that both of these are abelian. Because remember at the beginning of the course, we said that a group is abelian if you can see its table, if you have symmetry across the main diagonal. Symmetry across the main diagonal. And you can see easily with these colors that, you can see that both of these groups are abelian because they both have that symmetry. But one is cyclic and one is not. Z4 is generated by 1. So you can see here, if you have 1 plus 1 is 2. Now they're abelian, so I can just stay in this row. Add another 1, and you get 3. Add another 1, and we're at the identity. But over here, it is not cyclic. Every single element of the group generates a 2-element subgroup. So on your own, look at U5, U8, U10, and U12. Those are groups of 4. They're all abelian, and each of them will be identical to one of these 2. So you look at them and see, you're basically asking which ones are cyclic and which ones have all elements except for the identity of order 2. Just as in Z4, the cyclic groups of order 4 will have 2 generators. Here, 1 is a generator and 3 is a generator. You see 3 plus 3 is 2. And if we add one more, we get 1. And if we add one more, we're to 0. Add another 3. So we have 2 generators, and you will find, let me just tell you the answers, but I think you should put it on pause now and make sure you can do this. U5 and U10. U5 and U10 are cyclic, and U8 and U12 are isomorphic, or the same group as the Klein 4 group. You should be able to find both generators of U5 and both generators of U10. And we looked at this in class 2. Here are 2 groups of order 6, and you can see just looking at the tables that they are not abelian because there is not symmetry down the main diagonal. But you can see that they definitely are algebraically identical, coloring the identity red. And what these colors are doing for us here is giving us a mapping. They're telling us that if we have a mapping that matches E with 1 and R with 1, 2, 3 and R squared with 1, 3, 2 and so on, H with 1, 2, HR with 1, 2, 3 and HR squared with 1, 3, that this is a homomorphism. In other words, if you multiply, for example, let's just take one. Let's take HR times, no, excuse me, let's do R squared H over here. So I go R squared on the left and over to the column with H, and I get HR. Now over here, let's see, we mapped R squared to 1, I can't see that, 1, 3, 2, 1, 3, 2, and we mapped H to 1, 2, and if I multiply 1, 3, 2 on the left times 1, 2, I get 2, 3. Now look, HR was mapped, sure enough, to 2, 3. HR under our mapping went to 2, 3. You can see that this is a homomorphism. That's what the color coding gives us, is a correspondence, a 1-to-1, in this case, homomorphism of D3 onto S3. And we'll learn in a minute formally that if this homomorphism phi is 1-to-1 and onto, then it is an isomorphism. It establishes 2 groups are algebraically identical. I also gave you this in class. Here we have 2 other groups of order 6 that are, in this case, look at the symmetry. You see that they are symmetric along that main diagonal, thus they are abelian. And in fact, these groups are cyclic. Z6 is generated by 1, and you can see it. 1 plus 1 is 2. And then I want to add 1 to 2, and I get 3. And then adding, see, 1 plus 1 is 1. Yeah, plus 1, 3, 4, 5, 0. Now in U14, this was so trivial over there, but in U14, if we go 3 times 3 is 9. And now I want to multiply that by 3. Since the group is abelian, I can just go to the column under 9. 3 times 9 is 13. Now I want to multiply that by 3, so I'll go under the column for 13. 3 times 13 is 11, and 3 times 11 is 5, and 3 times 5 is 1. So another cyclic group, it is generated by 3 and by 5. That will give you the whole group. Notice every element of any group generates a cyclic subgroup. 3 and 5 generate the entire group. That's why it's called cyclic. The group is cyclic. But 9, if we generate the little subgroup here generated by 9, we get 9 comma, okay, 9 times 9 is 11, and 9 times 11 is 1. So as soon as we get to the identity, we're done. 9 generates a subgroup, as we proved on that test, a subgroup of order 3. Well, how about 13? Let's see the subgroup that it generates. We'll put 13 in. Now 13 squared, oh, we're to 1 right away. So 13 generates a little subgroup of order 2. And 11, if you do it, you will see that 11 also generates the same subgroup that the element 9 did. You'll find exactly the same thing in this group. You will have a subgroup of order 3, a subgroup of order 2, and the group itself, which is cyclic, of order 6. Now in a cyclic group, these are all of the subgroups. We're going to prove this later, but in a cyclic group, all of the subgroups are cyclic. So we know that U14 has exactly, well, 4 subgroups. It has, of course, the one generated by the identity, which is the trivial subgroup containing only the identity. It has one subgroup of order 3, one subgroup of order 2, and itself, U14 is the subgroup of U14. And you find exactly the same thing in Z6. Do keep in mind, as we saw on the test that we went over last time, is that in groups that are not cyclic, every element of the group generates a cyclic subgroup, but those subgroups are not necessarily all of them. For example, in D4, we had 7 cyclic subgroups, but we also had a subgroup of order 4 that was not cyclic. So you can go back and check that example. Only in cyclic groups can we say that all subgroups are cyclic. So here's the formal definition. If G star and G prime circle are groups, then a mapping phi from G to G prime is a homomorphism if it preserves the algebra. In other words, if phi of x star y is equal to phi of x circle phi of y for all x, y, and g. Now notice we will usually not be using these, we're not going to know what these, we'll know what the operations are, but we won't see them written. We're going to just say phi of xy is equal to phi of x, phi of y. You have to be aware of what groups you are in. For example, this xy is taken in G, so the operation would be star. This operation is right here, so that is an operation defined in G prime. So you have to be careful. You have to know where you are operating to know which operation you're talking about. If phi is 1-to-1 and onto, if phi is a 1-to-1 mapping and it is onto, in other words, the image of G is all of G prime, every element of G prime gets hit by the map, then phi is called an isomorphism. And that means that the groups are identical algebraically. And we denote that by G is isomorphic to G prime. And you use the same symbol you used for congruence in geometry. So how will we prove that one group is isomorphic to another? We certainly would not have access to their group tables all the time and be able to arrange them in identical ways the way we did for the simple groups of order 6 and order 4. we have to be able to use the mapping. So the first thing is we have to define a mapping. Step 1, define phi from G to G prime or from G prime to G. Define a mapping from G to G prime and show that phi of xy equals phi of x, phi of y for all xy in G. Now you can show it for all x, y, and g by just saying at the beginning, let x and y be in G. That makes them arbitrary. And then you show by using the map that you defined that the algebra is preserved. Okay, then step 2, we're trying to show, that means it's a homomorphism. Let me put, therefore, phi is a homomorphism. But then you have to show that phi is 1-to-1. Now how do we do that? Well, suppose, we've done this before, suppose phi of x is equal to phi of y for some x, y in G. And then show that this leads to x must be the same as y. And then number 3, you must show that phi is onto. In other words, the image of G is all of G prime, or that every element of G prime gets mapped to, or gets hit by phi. So here's how you do that. You say let, let's say z, let z be in G prime. In other words, it's an arbitrary element of G prime. And then using your mapping and what you know about G and G prime, find x, let's say, in G such that phi of x is z. Then you've shown that every element of G prime has a pre-image under phi. So we'll do an example. This is a problem. Let capital R be the additive group of real numbers. 0 is the identity, the operation is addition. And let R star be the multiplicative group of positive reals. So it is all numbers greater than 0, which is a group under multiplication. Identity is 1. So here it's very important to know the operations because the sets R star is a subset of R. So we want to prove that all of the real numbers under addition is isomorphic to the positive real numbers under multiplication. All right, so in this case, step 1 is half done. We don't have to think up the map ourselves. We're given the map, calling it f instead of phi. So f of x, this is the map. And we know, you can draw e to the x here. You see that the domain is all real numbers, and the range, or the image of the real numbers under the mapping f, is just the positive reals, not including 0. Okay, so we need to show that, now R is under addition, we need to look at f of x plus y. In this case, I use the operation because it's addition. So let's see, what will that be? That is e to the x plus y. And we know that that is e to the x, e to the y. We're just in the real numbers now. And, well, sure enough, that's f of x, f of y. So we have shown that f is a homomorphism. F is a, let's just say, hom. Therefore, f is a homomorphism. Now we need to show that f is 1-to-1. So suppose f of x is equal to f of y. Well, that means then e to the x is equal to e to the y. And we know that e to the x, the exponential function, is a 1-to-1 function. It's always increasing. This tells us that x must be y. So we can say, therefore, F is 1 to 1. Now we want to show that it is onto. So we have to let's call it Z. Let Z be any element of R star. Some positive real number. Okay, so we've been using R star before to be the non-zero reals, so excuse me here. This was what I saw in a book and I used the notation, but for this example we're letting R star be the multiplicative group of positive reals. I think maybe I should have just put a plus there. That might have been changing this to a plus. You would read it easier. Okay, so we pick a positive real. Now we want to find something that maps to it. This is the question we're trying to answer. In other words, we want e to the something equal to z, a positive number. Well, you know what that is. E to the natural log z is equal to z. So the natural log of z is a real number, and f of the natural log of z is equal to e to the natural log z, which is equal to z. Therefore, f is onto. So we showed that f is a homomorphism, that f is 1 to 1, and that f is onto. So we can conclude, therefore, that R, I'm going to put back in the operations just because it's the same, R under addition is isomorphic to the positive reals under multiplication. And the next problem, prove that if groups G and H are both cyclic of the same order n, then they are identical, they are isomorphic. So we need to define the mapping in this case, and then we need to show that it's a homomorphism and that it's a 1 to 1 and onto. So let's see, you wouldn't know where to start with this, so let's say that G, whoops, let me change color. Let's say that G is generated by some element A, and it will be then 1A, I'll say 1, well, let's make it E, A squared up to A to the n minus 1. And G prime is generated by some element, call it something other than A, and it is the powers of B. So we're going to get E after n times. B squared up to B to the n minus 1, and B to the n is E. Okay, so that's what it gave us. It gave us that they were cyclic groups of order n. So the first thing you do is give them some names and write it out so you get an idea. Now obviously you know the map you'd like to use here. You want to have E to E, A to B, A squared to B squared, etc. That's an obvious and natural map. So the question is, how do we say it? Well, let's let phi map G to G prime by phi of A to the k, every element of G is A to the k for some k, is equal to B to the k. And we know that k will be 0 less than or equal to k less than or equal to n minus 1. So that will be our mapping. That's obviously a natural mapping, but we need to make sure it's a homomorphism. So we say phi of A to the k, A to the j. In other words, two different elements of G is phi of a to the k plus j. But that's equal to, under our definition, b to the k plus j, which is b to the k, b to the j, and that is phi of a to the k, phi of a to the j. So we have, it is a homomorphism. So we got that. Phi is a homomorphism. First thing we need. Now we need to show it's one-to-one and onto. Well, in this case, there's really nothing to show. There's n elements in each group, and the mapping is clearly one-to-one. There's nothing to show here. It's clear just by what we drew right here. You can see clearly phi is both one-to-one and onto. So we have G is isomorphic to G prime. Now, what I want you to remember from this is that all cyclic groups of the same order are isomorphic. They are algebraically identical, whether they are generated by permutations, whether they're generated by rotations, or whether they're generated by numbers. It makes no difference. Matrices, matrix groups, if you have a matrix group of order 10 that's cyclic, it's isomorphic to Z10, and every other cyclic group of order 10. So keep that in mind. That's important. For example, we looked at these exact groups maybe on slide 2 or 3 and the one I gave you in class. You can see that these groups are isomorphic as soon as you see they are cyclic. U10 we saw was cyclic generated by 3, Z5 was cyclic generated by 1, and U5 was cyclic generated by 2. So these groups are all cyclic of order 5. Therefore, they are isomorphic. So let's prove our first theorem about group homomorphisms. You are responsible for all of these theorems, and moreover, look at the techniques used to prove them, because you will be asked on the next test and on homework to prove things that I have not proved before for you. So try to study with the idea of what tricks are used and how do I prove such things. I want to prove here that under a homomorphism, the image of the identity in G is the identity in H. In other words, identity maps to identity under any group homomorphism. So I need to show that. Well, if I want to show something is we'll have to use a property of identity. So let's just start with phi of G, phi of E in G, E sub G, the identity in G. And, we have to use the fact that this is the identity, and we have to use the fact that phi is a homomorphism. So let's write this as phi of E sub G, E sub G. Same thing, right? And that is phi of E sub G, E sub G, times phi of E sub G, because phi is a homomorphism. Okay, so now we have this. We have phi of E, the identity in G, is the same thing as itself squared, right? That's what we have here. Now, where do these things live? Where is phi of E sub G? It's in H, isn't it? So what we're saying is that this is an element of H. that is equal to itself times, well, is equal to itself squared. It's in H, so it has an inverse. I'm going to multiply both sides by phi of E sub G, whatever that is, inverse. And here, being careful to do it on the same side, E sub G inverse. It's an inverse in H. So when I multiply phi of E sub G times its inverse in H, I get the identity in H, don't I? And over here, I get phi of E sub G times the identity in H. So we have what we needed. Phi sends the identity in G to the identity in H. So we got it. Now the next one we want to prove is that it sends inverses to inverses. If it sends x to an element in H, it sends x inverse to that element's inverse in H. So to prove this, let's see, I know that x times x inverse is the identity in G. So I'm going to start out again with phi of the identity in G, and I'm going to write it as phi of x inverse, which is, because phi is a homomorphism, phi of x times phi of x inverse. Now we know that phi takes the identity to the identity in H, so phi of E sub G we know is the identity in H. This was by part 1 that we just proved. So this here tells us that this element, phi, if this element in H times this element in H gives us the identity, then we know that that must be the inverse of phi of x, because inverses are unique. So let's see, I guess we should write that, but let's see. So I'll say, therefore, phi of x inverse is equal to phi of x inverse, since inverses, and we're in H, I don't have to say that, but inverses in H are unique. Then there's a part 3 of this theorem that asks us to prove that phi of any power of x is mapped to phi of x to that same power. So let's see, I guess we'll have to use induction here. So let's let n be equal to 2. Clearly, when n is equal to 0, we have the identity. And when n is equal to 1, phi of x equals phi of x. So for n equals 0 and 1, there's nothing to prove. So let's let x be equal to 2. n is equal to 2. So phi of x squared equals, well, it's a homomorphism, phi of x, which is phi of x squared. So we're done with n equals 2. Let's suppose for some k greater than, let's say greater than 2 or greater than or equal to 2, phi of, let's say, phi of x to the k is equal to phi of x to the k. In other words, phi of the kth power of x in G sends it to the kth power of phi of x in H. We're assuming that's true, and now let's look at phi of x to the k plus 1. Well, that's equal to phi of x times x to the k. It's a group homomorphism, so that's phi of x times phi of x to the k. By our induction hypothesis, that's phi of x times phi of x to the k power, and now operating with powers of an element in H, we have phi of x to the k plus 1. Therefore, the theorem is true for all n greater than or equal to 0. So let me write that down. So phi of x to the n is equal to phi of x to the n for all n greater than or equal to 0. We proved that by induction. So now look at phi of, assuming still that n is positive, x to the minus n. Well, that's equal to phi of x inverse to the n. Now n is positive, so that is equal to phi of x inverse to the n by what we proved right here. And by our number 2 part of the proof, phi of x inverse is equal to phi of x inverse to the n, which is this, phi of x to the minus n. So therefore we proved part 3 completely by induction. Here we're going to prove that two groups are not isomorphic. You can see that we have the Klein-4 group here with 3 elements of order 2 and the identity, which has order 1. And we have is capital lambda 4, which is the 4th roots of unity. In other words, if you raise 1, I, negative 1, and negative I to the 4th power, you get 1. These are the 4 complex numbers that raised to the 4th power give you 1. Roots of unity, 4th roots of unity. So we want to prove that they're not isomorphic. Well, actually, lambda 4 is cyclic. It's generated by I. Let's just make sure that you see that. We start with I, we square it, we get negative 1, multiply by I again, and we have minus I, and multiply by I again, and we have minus I squared, which is minus negative 1 or 1. So you see that this group is cyclic. We want to prove that they are not isomorphic. We know all cyclic groups of order 4 are isomorphic, but let's prove that this one is not. All right, well, let's suppose that phi maps the 4th roots of unity to the Klein-4 group is a homomorphism. There's always a group homomorphism of some kind. It could just map everything to the identity. So suppose that phi is a homomorphism. We want to show that it cannot be one-to-one. So look at phi of I squared. We know that that is phi of I times phi of I, or phi of I squared. Actually, I think I should not be looking at phi of I squared. Let's look at phi of I cubed instead. Phi of I cubed is equal to phi of I cubed by what we just proved, the theorem. And notice that in the 4th roots of unity, this is v to lambda. This is lambda 4 to v. Notice in v, the phi of I lives in v, right? In v, if you cube each one of these, you get itself back, right? If you square this, just take this one here. If you square it, you get the identity. So if you cube it, you get itself. And it's the same for all three 2-2 cycles and, of course, for the identity. So phi of I cubed is phi of I cubed by the theorem that we just proved, which is the same thing as phi of I. It's an element of V. But phi of I cubed is equal to phi of minus I, because I cubed is minus I. So, therefore, phi of I cannot be equal to phi of minus I if it's 1-to-1. So phi is not 1-to-1, and we can say that this is true for any homomorphism that maps the fourth roots of unity onto V, onto the to the Klein 4 group, is not 1-to-1. So there does not exist a 1-to-1, an isomorphism from the fourth roots of unity to the Klein 4 group. So we can conclude, therefore, they are not isomorphic. I wish I could explain to you exactly how you dream up these ideas. You have to just fool around with things. Like at first I thought maybe phi of I squared equals phi of I would get me somewhere. But the problem is in V, our target group here, in V, everything squared is the identity. So it just didn't work for me. I turned this off and went over on scratch paper. So I thought, well, all right, there are no elements here that have a higher power, have a higher order than 2. But down here, I know that I has order 4, and that if you cube it, you get this, minus I. So if you cube everything else here, you get itself. So I thought, okay, I'm just going to start with phi of I cubed and see where it takes me. Well, by the theorem that we just proved, it's phi of I cubed. And by my knowledge of the Klein 4 group, I know that if I cube something, I get it back again. This is in the Klein 4 group. But phi of I cubed is phi of minus I, because of our knowledge of how to multiply powers of I. But we can't get the same thing for phi of I and phi of minus I if it was a 1-to-1 function. So here, phi was arbitrary. It was any homomorphism. And we showed that then no homomorphism can be 1-to-1, and therefore the groups are not isomorphic. The last example is we want to prove that C star, the non-zero complex numbers, are isomorphic to this set of matrices. It's all 2x2 matrices that satisfy, that have the same entry here, and additive inverses here and here. A and B are real numbers, and not all of them are 0. So we want to prove that they're isomorphic. That means we have to come up with a map. Well, there's a natural map. We know that every complex number is of the form A plus BI. So let's just let phi map C star to M star by phi. It's a natural mapping. A plus BI will go to, and let's just try this, go to the matrix A and then minus B, B, and we'll see where that takes us. We first need to show it's a homomorphism. So let's see, we are in multiplication in the complex. So phi of A plus BI times C plus DI then will be equal to, we need to multiply that out, phi of AC minus BD, multiplying the two complex numbers, plus BC plus AD. I'll put AD plus BC, I. Okay, well now we can perform the map. and that will be the matrix AC minus BD in this diagonal. And then here we have minus AD plus BC. And down here we have AD plus BC. Okay, we don't know yet if this is exactly what we want. Well, let's just leave it like that. This one's a bit more complicated to see. We're not just going to be able to go from this to what we want. Let's not put equals there. Let's just stop. We have that sentence, and now we will perform them separately and see if we get the same thing. Okay, so that was phi of xy, so to say, and now we will do phi of a plus bi times phi of c plus di and see if we get the same thing. Well, that would be the matrix A minus B, B times, and this other one goes to C, C minus D and D. So we need to multiply these two together, and we have AC minus BD, good. And for this entry, we have minus AD minus BC. That's the same. And then down in the second row, we have BC plus AD, or AD plus BC. And the last entry is minus BD plus AC, AC minus BD. So these are exactly the same. And we can say, therefore, phi is a homomorphism. We need to show that it is one-to-one and onto. So we'll show it's one-to-one first. Suppose phi of A plus BI is equal to phi of C plus DI. Well, that implies that the matrix AA minus BB is equal to the matrix CC minus DD. And we know that two matrices are equal if and only if all their entries are identical. So this implies that A equals C and B is equal to D, which certainly gives us A plus BI is equal to C plus DI, and we conclude that phi is one-to-one. Now we want to show it's onto. So we let A be a matrix in M star. So A would be of some form like this. Well, A minus B, B, A in M star. Well, clearly, then, phi of A plus BI is what gives us that matrix under the mapping. Here, I'll just put equals A. Therefore, phi is onto. And we can say that M star is isomorphic to C star.